for the second half of this? All good? All right. Okay, so as I said, you could be forgiven if you thought that the first two sessions were a little bit dull, or maybe things you'd seen before. Hopefully, in these next two sessions, the last two, we'll get more into some more interesting, or at least on the modeling side, things are closer to the cutting edge. Sound good? So in this part of the talk, or in this part of the tutorial, we'll talk about deep generative models, and in particular, the simplest deep generative model possible, which is called the Variational Autoencoder. So first, in this tutorial, I'll kind of explain a little bit, give a little bit of motivation for deep generative models. Explain what they are, why they might be interesting. We'll get into a little bit into a small amount of math, understanding how to learn deep generative models with Pyro's inference tools, the mathematical tools that Pyro implements. Once we do that, we'll dive right in, start implementing a simple deep generative model in Pyro, and performing inference in it, along with model learning. And finally, as I promised, we'll take a brief look at how inference algorithms, for example, the ELBO, are implemented in Pyro. And for those of you following along on your computers, the tutorials that the Pyro examples that this is based on are the VAE example and the introduction to stochastic variational inference, R1, which are on the Pyro website. Okay, so remember at the beginning, we talked about all these cool advances in AI and machine learning that were brought about by building rich, structured, customized probabilistic models and doing inference in them. The learning motor programs for handwritten characters, or inverse graphics, or learning to generate, or the automated statistician learning to generate interpretable models and entire analysis reports on the internals and the outputs of those models. And that allowed us to do all these really cool things, right? So remember, we were able to generate with this really powerful sort of structured handwritten characters model that was published in Science. We were able to generate in really a wide array of new sorts of characters. We were able to parse things into these interpretable latent representations, generate new examples of the same data, given only a single example of a class. We were able to generate images that were realistic enough to fool human judges most of the time. But the model that's actually doing all this here it's as you can imagine, right? It's quite complicated, and it's a testament to the folks who built its sort of perseverance and their attention to detail that they were able to get this to work. Right? It's got all these levels of primitives and subparts and parts, objects, types versus this type token distinction, which is a big thing in psychology. So this was clearly this represented an enormous amount of work on the part of especially the first author, who spent many years working on a collection of models like this. Spent most of his PhD. But what if we don't have a PhD's worth of time? What if we can't write down a good model? What if we don't know the subparts and the parts and the object templates, or whatever the equivalents are in the domain that we have? Maybe they don't even exist, right? Or at least in particularly some simple form amenable to being written down. Well, it's machine learning and it's 2018. So our solution to this, one sort of easy solution to this problem is to take all the parts that we don't know and replace them with neural networks and attempt to learn the parameters of those neural networks. And that's the essence of deep generative modeling, right? You've got probabilistic models that, where most or all of their components, are deterministic neural networks that parameterize latent variables that feed into other neural networks. And the goal is, given for example, a very large corpus of handwritten characters, as they used in the science paper, your goal might be to learn from scratch without putting any prior information in the form of hand engineering of the model. Your goal might be to learn a model that could generate images of equally high quality or generalize in equally powerful ways. The simplest possible form, sorry, I'm laughing at my own picture here, it's really bad. The simplest possible deep generative model, right? So here we could have replaced any or all of these components with neural networks and parameterize their outputs with random variables, with sample statements. But the simplest possible thing we could do is just say, you know what, forget the whole thing, forget any internal structure. Let's just say that our data is described by a single monolithic neural network whose inputs are random noise drawn from some simple distribution, like a bunch of independent normals, and whose outputs are the parameters of some final sample statement. And let's hope that, given a large enough corpus of data, we'd be able to learn to generate images that are of equally high quality or equally interesting. So just again, very briefly, to get into a little bit into the weeds of how we actually go about learning the parameters of all those neural networks, we have to revisit some of the ideas that we touched on in the middle of the last tutorial of the math of the ELBO. So in model learning, we have some parameterized family of models, right? A Pyro program with a bunch of components that are neural networks, where all of the neural network parameters are marked as Pyro parameters with pyro.param. And we'd like to adjust those parameters such that the probability of observing data, say that the handwritten digits, the handwritten characters, is maximized. But obviously we don't know this, so to compute the probability of generating a given data set, we have to integrate over all possible latent variables. Remember the sum and product rules. To get the distribution of one thing from a distribution of two things, you have to sum over all instances of one thing, or integrate in the case of a continuous space. And as you might expect, computing this interval directly is too difficult for most or really any interesting model. And so, once again, we'll have to resort to approximation. Right. So, let's revisit the definition of the ELBO, or the identity that I showed you in the previous tutorial. Remember, the ELBO was equivalent to this. It was equal to this constant that didn't depend on the guide, minus the KL divergence between the guide and the true posterior, which is what we were originally interested in that context. And I told you that we would talk about what that constant was later on. It turns out that constant, C, that doesn't depend on the guide, but it only depends on the model and the data. And it's exactly this model log evidence, log probability of x, the thing that we were interested in. X is the observed data. And again, remember that we chose the KL divergence because it was in part because it was non-negative, and it was 0 only when the guide was equal to the true posterior. Which means that here we've got the ELBO is equal to this thing that we're actually interested in minus a term that's always greater than or equal to 0, which means that this trusty old ELBO that we've been working with in the past two tutorials is actually a lower bound to the model's log evidence for any guide Q, depending on, and just the tightness of the bound depends on the goodness of the guide. And that's where the name ELBO comes from. So ELBO stands for evidence lower bound. See, the ELBO is a lower bound to the model's evidence. And so, just like we can use the ELBO for learning the parameters of a guide in exactly the same way, we can learn the parameters of a model, a deep generative model, by optimizing its parameters with respect to the ELBO. Exactly the same way. Okay. I told you we would pick the simplest possible deep generative model, which was this decoder network that I showed you, which is a neural network with some random inputs. And we're in keeping with this theme of simplicity. We're going to train it on just about the simplest data set imaginable, simplest non-trivial data set imaginable, which is this famous corpus of its handwritten digits, which are these little 32 by 32 images of handwritten digits taken from postage addresses written on letters or something in the 90s. In analogy with this motor programming model of handwritten characters, we'll try to learn a deep generative model of the simpler set of handwritten characters, these handwritten digits, which aren't as complex as the data set that we saw that was used in the science paper. So, what's the simplest deep generative model? What's this decoder network? Right, this thing which is takes some random inputs, feeds them through a black box, and finally samples some outputs. What does that actually look like in Pyro? Well, it's exactly as simple as it sounds. We sample some random noise, Z, some random inputs, which we're going to call the code of a particular data point. We sample those from this independent white noise distribution. We feed those through a neural network in a decoder here. And finally, we use the output of that neural network to parameterize a data distribution, which is, in this case, is a Bernoulli distribution, a coin flip for whether each pixel in our generated image is black or white. And this Pyro.module thing is just like Pyro. It just calls Pyro.program. So the neural network is in a decoder. There's nothing Pyro specific at all about it. Doesn't have anything to do with Pyro. It's just a completely standard PyTorch module. So those of you who use PyTorch, this will come as no surprise, or indeed any other deep learning framework. Those of you who haven't, I would encourage you to check out. PyTorch has a bunch of great documentation. And this Pyro.module function just goes through, it just loops through each of the parameters, the parameter objects that are attached to these neural networks, and calls Pyro.param to make the inference algorithm, SCI, inference by optimization, to make it aware of those parameters so that the optimizer can tune them according to ELBO. Okay, so that was easy. We have a model, 4 lines of Pyro. What about the guide? Well, we could start sort of the same way that we started before, right? Of having independent normal distributions for each data point, where guess for a given data point. So these latent codes Z are local to each image. They're not global. And so for each Z, for each data point, we'll guess that it's distributed according to the posterior, or is distributed according to the location, or a normal distribution whose location and scale are parameters, or free parameters that can be adjusted by an optimizer.
In that case, that is correct. Isn't that the desired property of the generative model, so that Z is, all the parameters are independent?
That's right. So it's an interesting that's an interesting point, because it's not true that the true posterior distribution of the Z's, like if you observe an image, an X, in the model, it's not true, for example, that it's not necessarily the case that the distribution is independent. We can assume they're independent. We can make an approximating assumption that they're independent, and that may help us actually learn a better model.
I thought that was the whole idea in generative models, that it kind of like widens the image, like every Z controls a different part of the image. So I know that the result might not be that, but this is the desire.
That's exactly right, and having guides just be regular Pyro programs allows us to build an assumption like that in. It's a form of regularization on the model that we learned. Okay, so in principle, so remember that so this is a very simple guide. It's sort of exactly like the one that we saw in the Bayesian regression example, although these Z's are local instead of global. We could attempt to proceed with model learning with that guide. But remember that I just go back to the ELBO here. Remember that the ELBO is the lower bound of the thing we actually want to optimize. And remember that the quality of the bound is determined by the quality of the guide. It's monotonic, in fact. The closer the guide to the true distribution, the true posterior, the closer the ELBO will be to the true log evidence that we actually want to optimize, to update the model's parameters. And so that means that we need to do, in principle, we might need to do, if we want our parameter updates to be stable and in the right direction, we might actually need to do guide learning for every time we update the parameters of the model. We might need to learn, and for each data point. Each time we update the model, and each time we see a new data point, we might need to repeat learning this guide for the particular data point over again. And if we look at how this might play out in a little SVI loop here, it's clearly, it seems clear that this wouldn't be computationally feasible, especially if the guide or the data set were more complex than the ones that we have. So here in this inner loop, this SVI guide is updating the parameters of the guide while the model parameters are fixed. And then this final step is taking one optimization step on the model parameters, while the parameters of the guide that we learned with this thing are fixed. And we have to repeat that, resetting those parameters in principle if we want it to be as close as possible to optimizing the right thing. And obviously this just won't do. It's just too expensive. So this is a very important idea, and I think I'll try to spend a little bit more time on it. Instead of doing this, optimizing new parameters from scratch for every data point, we're going to train a second neural network, we'll call an encoder, in analogy with our decoder neural network in the model, to guess the parameters of the normal distribution in our guide. So now the guide depends explicitly on the data, not only through the parameters, but it's actually a function of the data. And it no longer requires, now these encoder parameters, instead of being, so the parameters of this encoder neural network, instead of being local to each data point, like they were in our mean field guide, are now global. They're shared. The neural network encoder parameters are shared across all data points. And this means that we can actually take, rather than for each new batch of data, optimizing fresh parameters anew, we can spread out the cost of this optimization statistically across data sets and across iterations by updating the parameters of this encoder neural network once per set of data points, and keeping those parameters and updating the same set of parameters for all data points. And this idea is so in computer science, right? This general idea of paying maybe paying an upfront statistical cost in this case of not being able to immediately find a good guide for a given variable, but spreading out that cost across the data set is known as amortization. And using a neural network in this way is known in the literature as amortizing inference. So effectively we've replaced this little interlude here with a neural network, with a second neural network. Our encoder is now doing the job of this loop. And once again, encoder, something fancy about it. It's just another PyTorch neural network. It looks exactly like this, except sort of in reverse. And then we proceed as before. We prepare our model to be conditioned on data by wrapping it with condition or passing in data, and constraining it with an obfusc keyword argument, constraining our sample site X in the model to be equal to the images that we're generating. We create a wrapped PyTorch optimizer, this atom object. And we use the same loss that we've been using, this Pyro.infer.trace ELBO. And loop through our batch of data, and as you can see, if we plot the progress of the ELBO during training, it's going up. And actually, forgot to mention, so it's apparent in this code, it should be that now, rather than, if you remember this loop here, where we were alternating between updating guide parameters for a fixed model and updating model parameters for a fixed guide, now we're actually taking a single gradient step on both of those at once. This is safe. It's a bunch of computational cost, and this is a kind of a generally useful idea. And this is how we'll sort of proceed from here on with learning deep generative models. We'll update the parameters of the model and guide at the same time. Okay, so how do we do? Well, the neural networks we used were kind of crappy and underpowered. But nevertheless, if we take now our encoder neural network that we use in the guide, we feed in every image from the data, from the training data, and we do something like tsne, so which is takes these, in this case, these 20-dimensional latent codes, and embeds them so that we can visualize them in a two-dimensional space, which is what's plotted here. And then we color each of those points in that two-dimensional space by the class label. So each image is a handwritten digit from 0 to 9. If we color it by which digit if we color each point in this plot by each digit, or which digit it corresponds to, then we can see that the model and encoder have clearly picked up the class structure, which is a dominant source of variability in this data set. Right? It's clearly segmented into class-specific clusters. Similarly, we can generate things that look like digits. I think these are these could be much improved, especially if we used a fancy neural network like a small convolutional neural network as our encoder and our decoder. Yeah. Okay. So, see, this seems great, right? Like we've worked out how to do modeling. We've written a simple deep generative model and figured out how to do amortized inference. And we've actually gone through and done it and fed it to some data and plotted it. And almost all of this basically fits on a postcard or on a single slide.
Can I ask you a question? If we had an MLP, let's say, instead, okay, so we saw how we did, linear regression. So we had an MLP which was Bayesian, where the parameters were, random variables.
In a linear regression example?
Yeah, the linear regression was just like a linear regression, but if we just use, multiple layer neural network.
Yeah, okay.
We have no intuition about what, distribution
The posterior.
yeah, would be like, we chose normals, independent.
That's right, yeah. In that case, right, so Bayesian neural networks are an area of active research, and I would say honestly nothing works all that well. You're absolutely right that we don't have good intuitions, especially intuitions that we can put into a guide about what the posterior over those weights for a nonlinear regressor should look like. Which is why if you really need to use something like that, people in practice will use MCMC, Hamiltonian Monte Carlo, to get to do Bayesian inference over Bayesian neural network weights, because variational inference really doesn't work very well in that case. Precisely, I think, for the reason you pointed out, which is that we just don't have very good intuitions that we can put into a guide for what the results should be. Okay, yeah, so we have this, so pretty much all the code that we wrote for this example fits on a single slide, which is great. So it seems like there must be some complexity hiding somewhere, as there inevitably is. And a prime suspect, right, perhaps even well, certainly the biggest suspect is this, so far, still somewhat mysterious Pyro.infer.trace ELBO that we've used for training model and training guides. We've used this in all the examples so far. Maybe this is where all the complexity is hiding. Turns out that the answer is no. I thought it would be fun and useful, especially for people working with models that need more customized inference, to talk a little bit about how, just at the end of this part of the tutorial, about how inference algorithms in Pyro are implemented. And they're implemented on top of this library called Poutine, Pyro.Poutine, which I don't know if any of you have ever had poutine. It's this French-Canadian dish of cheese curds and gravy on top of French fries. It's quite good. So Pyro.Poutine is a collection of building blocks for modifying and recording the behavior of Pyro programs at sample and parameter sites. So you've already seen repeatedly condition, which sets the value of the sample site to be a particular value and marks it as observed, rather than or constrained rather than unconstrained. And there are others. For example, there's one called trace. There's a higher order function, an effect handler called trace, which creates a data structure, effectively a dictionary, containing the inputs, functions, or distributions, and the outputs found at each sample and parameter site in a single execution of the model. And then there's another is replay, which takes takes a dictionary of this data structure effectively is a dictionary of sample sites and values that you might get from trace. And in the course of, if you replay a model along along an execution history, then you replace the output in each sample site in the model with the output in this data structure that you pass in. And there are others. And we'll talk about the implementation details. But the upshot of all that is, even if you didn't, even if that was a little bit dense, the upshot is that thanks to the way the Pyro is built, Pyro inference code can be as compact and as readable as model or guide code. So here, using trace and replay, which I just described, I've implemented a very simple version of the ELBO, an estimator of the ELBO, which are called simple MC ELBO. And you can see all it's doing, right, is it takes the guide. So let's look at the definition of ELBO, right? It asks us to take this expectation says draw a sample from the guide Q and compute the probability of that guide along with the data and of that sample from the guide for those latent variables under the model, and the probability of those samples under the guide. Subtract them, and then take a bunch of samples and sum that up. Sum up those differences for each sample. And here, I've implemented exactly that logic for a single sample. So we collect a data structure, a dictionary that contains the inputs and outputs and distributions of all of the sample sites that we encounter in the course of executing the guide. And then we're going to see here, replay that data structure that we got from the guide. We're going to replay the model against that, which means that every sample site, every unconstrained sample site in the model now will return, instead of a sample from whatever distribution is there, it will return the value that's in this data structure that we got from the guide. And the data structure also provides computation provides a quick method for computing the probability of a single sample. These point estimates of the guide and model densities, which you can compute by taking all the distributions of the sample sites, computing the probability, the local probability of each sample site, and summing all those up. And finally, because the way PyTorch is implemented, PyTorch optimizers minimize loss functions. You keep taking steps. They add a sign to the gradient such that you're minimizing the loss function. So we just take our super simple ELBO implementation here and add a negative sign. And now there's no more flaw for boilerplate. We can use this directly in place of Pyro.Infer.Trace ELBO. So we were worried about, maybe Pyro's doing all this weird stuff under the hood, or the ELBO is this totally opaque thing. But in fact, as I said, inference code in Pyro can be and is designed to be as compact, extensible, readable, modifiable, hackable as model code is. This is also, I think, this ends up being important in practice, especially if you want to work with other sorts of loss functions, for example, or even modified ELBO. So I could take this implementation and add another line that added a regularization penalty, like an NL2 penalty for each of the parameters in the traces, and thereby automatically regularize. I'll add an NL2 regularizer to make sure that my parameters didn't explode. Okay, so I actually meant to finish this one a little bit early because I'd like to give myself a bit of a cushion on the next one. But just to recap, in this session of the tutorial, we got an introduction to this idea of deep generative modeling. Instead of instead of being able to write down really almost completely a description of how a particular data set might be generated or a particular model that we have in mind, we can also, just as we fill in gaps in guides that we can't write down by hand, we can fill in gaps in models with parameters that we can't write down by hand. And we took this idea and implemented a simple deep generative model in Pyro. We did variational inference model learning, so that we were able to learn a generative model of, in this case, handwritten digits. And then finally, we took a very brief look at how Pyro works under the hood. And in the next session, now that you've all seen the VAE, this variational autoencoder, we should now have the intuitions in place to start building up to more complex and interesting models. And we'll look at two case studies that are sort of small extensions from the VAE. That's it.
Okay, thank you. Let's give if you have questions, we can also take another, I think, is it time? Yeah, let's take a 5-minute break. And then we're getting to your last session, and we have the final presentation from